Okay, so for the first question here, rank the following carboxylic acids in order of increasing acidity, where 1 is going to be the most acidic acid, and then 4 is going to be the least acidic acid. Okay, so rank these acids in order of increasing acidity. 1 is the most acidic, 4 is the least acidic.
I think the third one is the most acidic, and then it's the last one.
And the last one is the second most?
Yeah,
Yeah,
second most acidic.
right?
And then it's the first one and then the second one.
Yeah. Nice. Because this is the most stable conjugate base when we deprotonate this carboxylic acid. This negative charge is the most stable because it's next to the most electronegative atom, fluorine, and there are more fluorine atoms in this third example than the last example there. So the induction effect is stronger here, right? This one here, like even though fluorine is more electronegative than chlorine, the proximity of this electronegative atom to the negative charge of the conjugate base takes priority, right? This electronegative atom here is closer to that acid, so that's why this is more acidic. Whereas these electronegative atoms here are too far away from that acid. Okay. Now let's do a similar one, but this time with carboxylic acid derivatives. Okay. Let's do this here. Okay, let's rank these carboxylic acid derivatives in order of increasing acidity, where 1 is going to be the most acidic and 5 is going to be the least acidic.
The most acidic is the carboxylic acid.
Right? Because this carboxylic acid hydrogen here is going to give us the most stable conjugate base when we deprotonate it and get that conjugate base on that oxygen right there, the negative charge on the oxygen. That's the most stable one because it's on the most like electronegative atom compared to like these here. And it can also do resonance with the carbonyl. So that's number 1.
And the next one is the ester.
The alpha hydrogen of the ester right here.
Wait, hold up. No, it's the acid chloride.
Yeah, the acid chloride alpha hydrogen is more acidic than the alpha hydrogen of the ester, right? But there is something more acidic than this alpha hydrogen here, right? You notice how
Oh, is it the amide, but it's the one with NH2.
Yeah, right. because the conjugate base is on an electronegative atom, nitrogen, right? Whereas if we put the negative charge on that alpha carbon there, that's less stable because that's a carbon atom. So this is number 2. Right. So which one would be number 3?
3 would be, is it the acid chloride?
Yeah, acid chloride. Because if we drop the conjugate bases of all the other ones here, this conjugate base with the negative charge is the most stable because it has the least competition. It could do resonance with the carbonyl all to itself, because this chlorine here is not going to do resonance with the carbonyl since it's too electronegative, and also the orbitals do not overlap well.
And then it's the ester.
And then last one, amide, tertiary amide, right? These amides are different because there is no hydrogen on that nitrogen on the tertiary amide. So the most acidic hydrogen is actually that alpha hydrogen right there. But for the primary amide or even secondary amide, if there's a hydrogen on that electronegative nitrogen, then that makes it more acidic than the alpha hydrogens, right? But the reason why this carboxylic acid is more acidic is because the negative charge is on a more electronegative atom here, oxygen, making this number 1. Okay, now let's do ranking the base question now instead of acid. Okay. Now, rank these following molecules in order of increasing basicity, where 1 is going to be the most basic molecule, 3 is going to be the least basic molecule.
Most basic is the amide.
Yes, that's going to be number 1.
And then it's the ester and then acid chlorine.
Yeah. Right. Because we see that this amide here, nitrogen is the least electronegative, making it able to donate the most electrons, making that oxygen there the biggest negative charge. Chlorine, the carbonyl oxygen, is the smallest partial negative charge because chlorine is so electronegative, it doesn't want to like donate its electrons. And then oxygen is in the middle. It's the intermediate. Right? And the bigger the negative charge you have, the more basic the molecule is going to be. Okay, now let's do some predict the product reactions and then synthesis problems. Okay. Let's say we have okay, think about this one here.
Is this Jones?
Yeah, this is Jones reagent.
So, okay, so
Chromium.
that is a strong oxidizing. So this goes to carboxylic acid.
Yeah, strong oxidizing agent reacting with a primary alcohol goes to a carboxylic acid. What if that was a secondary alcohol? What functional group would you form?
Ketone.
Yeah, ketone. Huh. Okay, let's do this one here. And you could also walk me through the mechanism if you get stuck here. Like, what would be the first thing that happens, and the arrows.
So this is acid, so something has to get protonated,
Mm-hmm.
and I think it's the nitrogen that gets protonated.
Right. So if we protonate the nitrogen here, right? I think you're thinking of that because in all the previous examples, we said nitrogen is more basic than oxygen, since nitrogen is less electronegative, more willing to donate electrons and attack. But this nitrogen here is part of a functional group. What is this overall functional group here when it's next to a carbonyl?
Amine.
Amide, right? And all the carboxylic acid derivatives, which is like an amide, ester, acyl halide, or anhydride. What did we say was the most basic atom? The carbonyl oxygen or the leaving group one, and why?
The
Think
most
about the
basic.
and think about the conjugate acid. Like, what's going to give you the most stable conjugate acid? Which one can do the most resonance?
The nitrogen could do resonance.
Right.
Oh, so
So
then that makes it more stable. Okay.
if we protonate the nitrogen, right, this is the conjugate acid we get. Does that make sense so far? Like how this nitrogen like gets protonated to get this conjugate acid here with the extra hydrogen?
Yes.
Yeah. This one right here, it cannot do resonance, right? Like no resonance at all. But if we protonate the carbonyl oxygen, this can do resonance.
Because the lone pair from the nitrogen.
Yeah, can go down there and then pop the double bonds with oxygen right there. Right? You know how like last time you said you tried to make a double bond right there by shifting this double bond there? That would break the octet rule. So that's why we can't do that.
Oh, okay.
Right? So any carboxylic acid derivative, the most basic atom is always going to be the carbonyl oxygen. So if you see strong acid, the carbonyl oxygen always gets protonated first. Right? If it's an ester, the carbonyl oxygen gets protonated first. Carboxylic acid, acyl halide, anhydride, amide in this example, the carbonyl oxygen always gets protonated first. Okay, once that happens, what happens next? We activated the carbonyl carbon, making it a stronger electrophile. Now, what can attack that strong electrophile now?
The water.
Yeah, the water, H2O. To get this tetrahedral intermediate right here. Right, now what do you think happens next? This is the proton transfer step where we like deprotonate the group we want to keep and then protonate the group we want to kick out.
Deprotonate. Is it, are you deprotonating the nitrogen or no?
The
Because you
nitrogen
want to
here,
kick out the, wait, hold up. Let me look at this. Okay, so we just added the H2O, so we are keeping that because it doesn't make sense to kick it out if we just added it.
yeah.
So that means we are kicking out, deprotonate something to protonate something else. So are we deprotonating that, the OH2 plus?
Yeah, we want that to stay because we just added it. And the group that we want to leave is this nitrogen here, the amine group right there.
Oh, okay.
Right. And most professors, they want you to do it one at a time, like where you deprotonate this first and then protonate that afterwards. But to save time, we can do that at the same time. We could protonate this nitrogen and deprotonate this oxygen at the same time like that. Okay. Since this is like for the DAT, the mechanism arrows would not matter here. You still get the same thing. Getting to this point here. Does this make sense so far? How I got to here, right? And then now once we have a good leaving group, we could reform the carbonyl. This bond here is going to break and kick out that nitrogen right there. But it doesn't fully leave because this is part of a ring. We just broke open the ring where the amine is still part of the molecule, but it's now a linear branch, linear chain, right? Where this is the carbonyl that just got reformed. The oxygen is still bonded to the hydrogen right there, OH. 1, 2, 3, 4, 5 carbons, and then the nitrogen. So this is 1, 2, 3, 4, 5 carbons, and then the nitrogen right here, NH2. 1, 2, 3, 4, 5. That's the NH2 here. Now the very last step is to neutralize this carbonyl oxygen by deprotonating it with some kind of base, which in this case is going to be HSO4 minus, giving us this final answer here. Right. 1, 2, 3, 4, 5. And make sure to keep track of the carbon atoms, because a lot of students forget one carbon or add an extra carbon, right? But to keep track of the carbons, it's useful to number them and the relationship between the functional groups, right? We see that's 1, 2, 3, 4, 5. We have to make sure that this is also 1, 2, 3, 4, 5, like that, to not add an extra carbon or lose a carbon on accident when we redraw that product.
And what is this reaction called?
This is hydrolysis of nitrile, amide. Hydrolysis of amide to carboxylic acid.
Okay. What does the heat
Hydrolysis.
do, or is it just part of the reaction? Or reaction?
Heat
Wait,
is
react.
reactant, yeah, it's part of the reaction, and it's required for amide because amide is one of the lower reactive derivatives, right? The things that do not require heat are the top two most reactive derivatives. And what are the top two most reactive derivatives that do not require heat, acid or base? That it could just react with any neutral molecule by itself. It doesn't need to get activated. It doesn't need an acid or base. It doesn't need heat as extra energy to go
Is
through.
it acid and hydride?
Acid and hydride is one. That's the second most reactive. There's one more that's more reactive than that one.
Acid chloride?
Yeah, acid chloride or acid bromide, or in general acid halide. So those two derivatives, acid halide and acid anhydride, do not require heat. They do not require acid. They do not require base catalyst. But the lower reactive ones like carboxylic acid, ester, amide, nitriles, they require acid or base catalysts and heat for extra energy. Okay. Okay, let's try this reaction here.
CH. Okay, so do you have to use the acid to protonate something first?
Yeah,
no?
we have strong acid. So acid-base reaction is going to happen first because it's one of the fastest reactions in OChem. So what's going to get protonated here? What's the most basic atom in this starting material?
You said the carbonyl oxygen is the most basic for derivatives.
Right. For derivatives, that's the most basic atom. So that's the one that's going to get protonated first. Right. Once we protonated this carbonyl oxygen, we turned this weak electrophile into a strong electrophile here.
Wait, can we go over why the carbonyl oxygen is the most basic again?
Yeah, the carbonyl oxygen is the most basic one because when we protonate it, this is the conjugate acid we get, right? But if we protonate the alcohol oxygen with the acid, the conjugate acid that we will get is this right here. Right? which conjugate acid is the most stable and why?
Most stable would be, I think it's the plus on the methoxy,
Right. And why do you say that's the most stable?
because the CH3 is a electron donating group.
Oh yeah. So inductively, this CH3 here will donate electrons to the positive charge, making it stable. But this one here is actually more stable because it could do resonance. This pair of electrons on the oxygen there can go down and pop that double bond onto the oxygen right there for resonance. But there is no resonance here. We cannot shift this down because that's gonna break the octet rule.
Oh
Right?
yeah.
So resonance overpowers the induction effect, making this the more stable conjugate acid coming from the most basic atom there.
Okay, so after you protonate that, it's now activated, so you could use the alcohol to attack the carbonyl carbon.
Right. And this alcohol here, what would it look like in bond line structure?
So draw a dot for a carbon, and then you would draw one carbon going up, one going to the left, and a OH going to the right, and then another line from that center carbon for the H.
Right. And we can leave that as invisible. We don't have to explicitly draw that out because it would be invisible. Right. Where the nucleophile is going to be the alcohol oxygen that is going to attack that carbonyl carbon and pop the carbonyl onto the oxygen right there. Before, this weak neutral nucleophile could not attack this weak electrophile. We had to activate it by protonating it first, turning it into a strong electrophile for this weak nucleophile to be able to attack that strong electrophile there. Right. Once we do that, we are going to get this tetrahedral intermediate here. Where the oxygen that attacked this carbonyl carbon is this oxygen right here, and this is the carbonyl carbon that got attacked. This is the new bond between them, right? Now, what is going to happen next? What's the proton transfer step here?
Protonate the methoxy,
Protonate the methoxy and deprotonate
the O that has a plus.
yeah, right. And I'm just gonna do this in one singular step to save time here. Right. This is now a good leaving group. This is a bad leaving group. We could reform that carbonyl and kick out that good leaving group to get this structure here. And what's the last step here in the mechanism?
Deprotonate the carbonyl oxygen.
Yep, to make it neutral. And what functional group did we just create here in the final product? What is this functional group here?
Ester.
Ester, yeah. We started with an ester. We ended with a different kind of ester. What is this reaction name? When we
What's the first letter?
T.
T?
Yeah, reaction is T. When we start with an ester and we create a different ester. What word is like different? Right. So same is cis, different is going to be
Trans.
trans. Trans esterification. There is another esterification reaction, but the starting material would be carboxylic acid. If the starting material was like carboxylic acid and you create an ester from that, what is the reaction name?
Fischer esterification.
Yeah, Fischer esterification. Fischer esterification is when you start with a carboxylic acid and you create an ester. Trans esterification is you're creating a different trans ester from an ester. Any questions on this?
No, I'm good.
Okay. Now let's do. Okay, let's do this predictive products reaction.
What is P trace?
P trace is trace of phosphorus or trace of PBr3.
Oh, okay.
PBr3 trace.
Wait, PBr3. So does this replace the OH with Br?
Yeah, it would if we don't have trace amount of it, right? If we have an excess amount of PBr3, then it would create an isobromide from this carboxylic acid, but we have trace, so it would do something else. I'll give you the reaction name, HVZ or Hell-Vorhard-Zielinski reaction.
Is it bromination?
Yeah. Bromination on what carbon
Alpha
specifically?
alpha
What?
carbon?
HVZ is always going to brominate the alpha carbon, or alpha bromination, which is this alpha carbon here. We just add a bromine right there, and that's it.
Is this by radical or something else?
I have to check the mechanism. The mechanism is pretty long, but I don't think the DET is going to test the mechanism. It's just going to test you recognizing the reagents and what reaction it does, and then predicting the product of that, or going backwards from the reactant, like predicting what the reactant came from. The mechanism is pretty long. I have to look it up to see if it's a radical involved or some nucleophilic acyl substitution or some weird migration step for the mechanism. Okay. Now let's do. Okay, let's try this 5-step multi-steps predictive products question here.
So Jones is a strong oxidizing agent, so it turns that primary alcohol to a carboxylic acid.
Yes, carboxylic acid after the first step.
And then the next step replaces the OH with the Cl.
To create the acyl chloride, the most reactive carboxylic acid derivative.
NH3. Does this deprotonate something? No, right?
It will not deprotonate something, but it will replace the Cl with an NH2, right? And what is this functional group here that we just created here?
Amine.
Amide, which is a lower reactive derivative than an acyl chloride. And we said that acyl chloride can create any of the lower reactive derivatives in one step, right? To create an amide, we use the neutral version of the leaving group. To create an ester, we use an alcohol. To create a carboxylic acid, we use water. To create an anhydride, we use carboxylate. And what kind of amide is this? Primary, secondary, or tertiary?
Primary.
Yep, primary amide reacting with Br2 base and water is what kind of reaction? This is one of the other weird reactions for this carboxylic acid derivative section.
Is this similar to the other one that we just did or no?
It's similar in that the mechanism is weird and the reaction is weird, but it's not going to be the same as the other one we just did.
But do we end up with a acid bromine?
No, we don't end up with acid bromide.
Does a bromine get added?
No bromine gets added.
Oh.
I'll give you the reaction name and then maybe it will click. Hoffman rearrangement.
I don't think I remember this one.
This one here will get rid of a carbonyl carbon and convert this whole primary amide here into a primary amine. Just like that, where we have this primary amine right here that's substituted this primary amide. And you notice how that carbonyl carbon there is eliminated now? That's why we lose one carbon. This material here had 7 carbons, 1, 2, 3, 4, 5, 6, 7. But once we did Hoffman rearrangement, we got rid of 1 carbon. We only have 1, 2, 3, 4, 5, 6 carbons now. So
Okay.
Hoffman rearrangement will turn a primary amide into a primary amine and lose 1 carbon in the process.
And it only works with primary amides?
Yep, it only works with primary amides.
Okay. Okay, so once we have that, then the last step is this EAS?
Not EAS, because this is our benzene group here with the acyl group, but we don't have any metal catalyst. We don't have AlCO3 or FeCO3 here. So this is NAS, nucleophilic acyl substitution. Right. So what functional group is this reagent here?
Acid chloride.
Yeah. And what functional group is this material here?
Amine.
Amine. Acid chloride and amine reacting together creates what kind of functional group? What kind of derivative?
What kind of derivative?
It's similar to this reaction here, right? Where we had an acid chloride reacting with an amine. If that comes together, what functional group is formed?
Oh, amide?
Amide. So another amide is going to get formed here. The chlorine gets substituted with the amine here that we have. Right? But this is different now because the starting material in this part is the acid chloride. The reagent is the amine. but for this part here, the starting material is the amine, and then the reagent is the acid chloride. That's the same reaction though. It's just shown differently to create the amide here.
Okay, that makes sense. What is that reaction called? The acid chloride to amide?
Acid chloride to amide is amide formation from acid chloride. There's no specific name for it. It's just like, yeah, amide formation from acid chloride.
Okay.
Nucleophilic acyl substitution. That's the mechanism type. Okay, let's do some synthesis problems here. Okay. Okay, let's try the synthesis problem right here.
Is this some kind of substitution?
Substitution, like SN2 reaction, SN1 reaction.
Yeah.
We see that the bromine got substituted with the ester, right? But if that were to happen, we would need to have a negative charge on that carbonyl carbon right there. But that's impossible because we cannot have that negative charge on the carbonyl carbon. That carbonyl carbon is positively charged because that oxygen is there. But what is this derivative here? What functional group is that?
Ester?
Ester. And what could we say that comes from? What's the parent functional group?
Carboxylic acid?
Yeah, carboxylic acid, right? So let's say that this is the carbonyl carbon of the carboxylic acid. What is a method that can create a carboxylic acid with an extra carbon in the starting material? Here. Like, how can we create a carboxylic acid with an extra carbon? Right? Because we want the extra carbon right there. There's two methods.
But can't you use another kind of substitution
To create carboxylic acid?
to, I don't know, I'm using my climbing method. So like you just add an extra carbon and then, okay, never mind. I'm
Yeah, so
overthinking.
the two methods are Grignard reaction with carbon dioxide or hydrolysis of nitrile. Right. So let me give you the two methods here. Let's say we have a primary alcohol, right? And we wanted to, well, not primary alcohol. Let's say primary substrate with a good leaving group, bromine. And then we wanted to create this carboxylic acid here, where at the starting material, we had 2 carbons, but in the end product, we have 3 carbons. Right? We can do this in 2 ways. We can convert the starting material into a Grignard reagent with Mg, creating this MgBr. And then this carboxylic acid here can be formed from CO2, carbon dioxide there, first step. Second step, acid workup, right? Because this star here will attack that dot, pop that down there to create O minus, and the O minus will get protonated by H plus. That's the first route. The second route
the next one substitution with a CN?
Yeah,
no?
substitution with a CN, NaCN or KCN. Right? To create this CN right there, where that's the extra carbon. And then what can we use to create this carboxylic acid from the CN? How can we transform the CN to this carboxylic acid here?
Do you just use an oxidizing reagent?
Non-oxidizing agent, because this is not alcohol. A nitrile is a cousin of the derivative, so we have to use hydrolysis using H2SO4, water, and heat. So acid, water, and heat. If this was a primary alcohol, then you would use an oxidizing agent like Jones. But this is a nitrile, which is a carboxylic acid derivative that could get hydrolyzed into the carboxylic acid using acid, water, and heat, just like any other derivative. Right. But there are limitations for both cases. Right. For the trial case, since we're using acid, water, and base, this will also react with alkene. And SN2, which will only perform with primary or secondary substrates. Tertiary substrates are too sterically hindered, so it will do that. Right? But for Grignard reagent, this Grignard reagent is a strong base, strong liquefied, so it will react with acidic hydrogens that are present. Right? So based on the starting material here, which route do you want to go for?
Since there's a alkene in the starting material, that means we can't do the one that involves substitution with a nitrile group.
Yeah, to go with the
So we have to do
Grignard route.
Grignard.
Yeah. Mg to create this MgBr, CO2, second step, acid workup to create the carboxylic acid. Right. Now, how can we create this ester from this carboxylic acid here?
Oh, wait, didn't we go over this earlier? It was like Fischer esterification.
Yeah, Fischer esterification, but what is required in the reagent for Fischer esterification?
An ester?
That's the product that we want to go for, but what's the functional group of the reagent to create that ester?
Carboxylic acid.
Carboxylic acid is the starting material. The reagent is going to be an alcohol, right? Where the OR group of the alcohol is going to be the OR group of the ester there. And what conditions do we have to work with for this reaction to go through, acidic or basic conditions?
Acidic.
Acidic. And why cannot we work in basic conditions?
Because it's gonna deprotonate the carboxylic acid.
Yeah, it's gonna deprotonate the carboxylic acid. But we said earlier that if we are in acidic conditions, it would react with the alkene, right? Because acid will react with the alkene to hydrate it, Markov composition of an alcohol. So we cannot do Fischer esterification here, right? Because if we do H2SO4 and heat or something like that, the H2SO4 will react with the alkene instead. Right?
Oh yeah.
We cannot do Fischer esterification here because it requires an acid catalyst. But we said that the alkene there does not want to react with an acid because it is unreacted there. So we have to do some other route. Okay. Let's say this came from the most reactive derivative, acyl chloride. Right. This is the most reactive derivative here, meaning that it does not require heat. It does not require acid or base catalyst. We could just use a neutral alcohol there. No acid needed, no base needed, right? Now, how can we convert this carboxylic acid into this acyl halide here?
SOCO2.
Yeah, SOCO2. Right. So we cannot use Fischer esterification here because the acid will also react with the alkene. Let's do this one.
Wait, then how do we change the Cl into an oxygen?
Yeah, so the Cl will get converted into an OR from this alcohol here, right? Where the mechanism is that this oxygen here will attack that carbonyl carbon, peptidyl bonds with oxygen, to create this tetrahedral intermediate here. Right. This carbonyl carbon here did not have to be protonated or activated because it's already a very strong electrophile. In the other examples, we had to protonate it or activate it, like in ester or amide or carboxylic acid, because that was a weak electrophile. But acyl halide or anhydride is a very strong electrophile. A weak nucleophile can just attack it right away, creating this tetrahedral intermediate. Then we could reform the carbonyl and kick out the good living group chlorine there. And then that chlorine that left can come back to deprotonate that hydrogen. I mean, yeah, deprotonate this oxygen here to get to the final product there, the neutral product there.
Oh, okay.
Yeah, that's why we don't need acid here, because this is already a very strong electrophile. It just gets attacked right away. No acid needed. So this alkene would be unreacted. I'm gonna leave these two routes at the bottom because the next synthesis problem is gonna test something very similar. Okay, let's try this synthesis problem here.
Okay, we said before that, or this was pretty similar to the other one in that we can't do substitution because there's going to be a negative charge on the carbonyl carbon.
Wait, we can't do what again?
Substitution?
Substitution with the NaCN.
Wait, what? Oh, okay. I guess you can do it because you don't have an alkene.
Yeah, we can do it because we don't have an alkene. Right. And heat. So we can do NaCN or KCN to substitute it. But why can't we use the Grignard route? Right? Like, what's the problem if we try to put this into MGBR? What would happen?
It will deprotonate the alcohol.
Yeah, it will deprotonate the alcohol, but we don't want that because the alcohol is unreacted. So we can't use the Grignard route in this example. We have to go with the nitrile route. And then we can hydrolyze that with acid, water, and heat to get this carboxylic acid here, right? Where this is the extra carbon here that we added, and the extra carbon comes from the nitrile there. Now, how can we create this amide here? The best way is to go to the most reactive derivative and then make any lower reactive derivatives in one step.
Make it go through a what? A derivative?
The most reactive derivative.
Oh, the most reactive. Acid acid halide.
Yep, acid halide.
So that means you could do wait, no. If you do SOCl2, wouldn't it replace the other OH too?
Oh, right, it would replace the other OH as well.
So
But there is a way to protect the OH. So let's see. Yeah, there is a way to protect the OH. So we have to use some protecting groups here. This is gonna be like alkene reaction. So we could use this alkene with H2SO4 to protect the alcohol and create this structure here. Right? Because what happened here was that this acid reacted with the alkene, right? Which carbon gets protonated? The one on the left or the one on the right?
the one on the right, because it's tertiary.
The one on the right is tertiary, so we want the carbocation there, right? If we want a carbocation there, we want that to lose a bond. So to make that lose a bond, the one on the left gets protonated, right? The one on
Oh
the left,
yeah, that's what I was thinking.
yeah, like the carbocation on the middle, right? Gets formed where that carbocation there will get attacked by that alcohol right there to create this ether here, right? Where this is the carbonyl carbon that got attacked right there, and that's the new bond between them, right? And then we could do SOCO2, which will not react with the ether, but we will react with the carboxylic acid to create the acyl halide. And then to create that amide right there, we could use this amine and two equivalents of it because a second equivalent is needed to deprotonate the very end product to create this amide. And then from here, we could deprotect this ether by using this is the amide here, acid and water, right? If we put heat there, that's gonna be a problem because if we put heat there, what else would happen?
Mm,
Right? The acid and water will deprotect the ether back into the alcohol, but if we put heat there, something else would happen as well in this material here.
condensation?
Not condensation, but hydrolysis of amide into carboxylic acid. Because you know how amide is the lowest reactive derivative and nitrile?
Wait, I thought that only works with if you have like a benzene.
No, it works with any amide.
Okay.
Yeah, this is a type of amide which can get converted back to a carboxylic acid if we use H2SO4, water, and heat. Right, but if we don't have heat, this amide would not hydrolyze into carboxylic acid. Right, where we just put acid and water with no heat, and that will just react with the ether, converting that into alcohol.
What's the one? I think I'm thinking of the one where you have a benzene ring, and then if you have any alpha hydrogens at all, then it's gonna turn to carboxylic acid. I think was it KMNO4 or something?
Oh yeah, that's KMNO4.
Oh,
Yeah,
okay.
yeah, that's when you have a benzylic hydrogen. It converts that R group into carboxylic acid. Yeah. That's oxidation of benzylic hydrogen. This is hydrolysis of amide, hydrolysis of a carboxylic acid derivative.
Oh, okay.
Like ester, amide, nitrile, anhydride, acyl halide. When we react that with water or acid and heat, then that gets converted back to carboxylic acid. It depends on the type of derivative. But for this specific type, amide, one of the lowest reactive derivatives, we need heat. We need heat and acid and water to convert it back to the carboxylic acid. But because we don't have heat here, that amide stays as an amide, which is good.
And then we're done.
Yeah. And that's the last step. Okay. So that was the carboxylic acid derivative stuff. What other sections do you want to go over?
Wait, what else did you say you have?
I also have the hybridization, sigma bond, pi bond, and formal charges, and also SN2, E2, SN1, E1, alcohol ether reactions as well.
Okay, let's do that one then, the last one.
Okay. Let's see. 1, 2, 3, 4, 5. Okay, let's do 5 of the SN1, E1, SN2, E2 reactions, and then move on to alcohol ether reactions, and then enantiomers, diisomers, constitution isomers, meso molecules, identical molecules as well. Okay. Right. I'm gonna give you 5, and then you try them out, and then I'm gonna take a 5-10 minute break.
Okay.
Okay. Try these 5 here.
The first one has a strong base, right?
The first one, NaN3. The thing is N3 minus. N3 minus is a weak base, strong nucleophile.
Oh, okay.
Right. An N minus is a strong base, but there's no R here. It's just N3 minus. N3 minus is a weak base, strong nucleophile.
I always get mixed up with base and nucleophile.
Oh yeah.
Wait, so how can you tell like which one's which again?
The strong base is going to be like RO minus or RNH minus or R2N minus or like a negative charge on an oxygen or nitrogen, but the nitrogen and oxygen also has an R group attached to it. This is a negative charge on a nitrogen, but there are no R groups there. So that's why it's a weak base, strong nucleophile. All of these are also strong nucleophiles, strong bases, strong nucleophiles. And the 3 types of weak base, weak nucleophiles are water, alcohol, ROH, and carboxylic acid. all of them are neutral, making them a weak base, weak nucleophile. ROH is different than RONA or ROK because there's no negative charge on ROH. And then the
So
weak base strong nucleophiles are like N3 minus, CN minus, BR minus, I minus, CL minus. Yeah, those are the common weak base strong nucleophiles like NaCN, NaN3, or KCN or KN3. Those are the common weak base strong nucleophiles.
first one does SN2.
Yep. Try
So
the 5 on your own, and then let me know when you finish. I'm gonna take a little break.
okay.
Oh yeah, thanks for the Skittles, Tommy.
Oh yeah. Okay, I just got my iPad so I could draw it out.
Your iPad just died.
No, I just got it.
Um, Which part are you on? Which question?
The fourth one.
Okay, okay. Let me know when you finish all 5.
Yeah. Done.
Mm-hmm. Nice. I'm gonna erase the red. Do you still need the red?
No.
Okay, walk me through these questions here, like how you thought about these. Like, what's the substrate? What's the base? What's the nucleophile? Is there a good leaving group present? What's the reaction? The arrows.
So the first one is a weak base, strong nucleophile, and it's in a protic solvent.
Mm-hmm.
So you do SN2. So you would invert, or when you add the N3, you invert the dash
Stereochemistry.
to wedge.
Yep. Wedge and 3. Is this what you got?
Yeah.
Yeah, that's right.
Okay, the next one is a weak base, weak nucleophile. So you would have to make the Cl leave first to make a cation,
Right.
and then you do rearrangement because you could have a more stable cation by doing a hydride shift.
Mm-hmm.
And then from there, you would have the alcohol attack the carbonyl.
Carbocation.
Or
Carbocation.
yeah, I mean,
Right,
oh
right.
my god,
Uh-huh. All right. And then what's the last step of the mechanism here once that
you
happens?
deprotonate it with the Cl minus.
Yeah, Cl minus or another alcohol, it doesn't matter. You could use either or to get the neutral ether here. And what is this reaction called specifically? Once that we just did to get this final product here.
SN1.
SN1, right? And what other reaction always goes with SN1?
I mean E1.
E1, right? Where E1 is gonna have the same exact starting steps as SN1 up until we get to the most stable carbocation after the rearrangement step, right? But at this point, what would the arrows look like for E1?
Then it would, so the alcohol would deprotonate the one, two, the carbon on the right of that carbocation, but it deprotonates the hydrogen. Yeah,
Yeah,
that one.
and it makes a double bond right there from
Yeah.
that bond to create this alkene here, which is our E1 product. And it's minor unless you have heat, and SN1 will be major. So those are your two products, SN1 and E1, where SN1 is the major one. Right. Okay.
And yeah.
I'm gonna erase this so we have more space for
Okay.
the other three. It's the other three. are now going to be under the same reaction umbrella, but there's different types of that. Right, this last reaction here is like the hardest compared to like these four, because a lot of factors are going to come into play. Okay.
That's a strong base.
Yep. Negative charge on the OR, strong base, strong nucleophile.
So you would deprotonate a hydrogen, but it's going to be on the left one right now.
Yeah, the left one, but what is the stereochemistry of the hydrogen on the left one?
It is a wedge.
A wedge. And for the mechanism of the E2 reaction, it's anti-periplanar transition state. Is this beta hydrogen anti to the leaving group?
No.
No. So what can we do to make it anti to the leaving group?
Rotate.
Yeah, rotate
signal
this
bond.
signal bond between them and swap that methyl with the ethyl right there to create this rotated structure here, right? Where I just swapped that methyl and ethyl group. That methyl group is now there. The ethyl group is down here. Does that make sense so far?
Wait,
Like when I swapped it, it will also swap the
oh, yeah.
stereochemistry, like the dash to a wedge. And to make sure that this is correct, you could do R and S. Like this is a chiral center here. If you assign R and S there, that has to stay R or S as whatever it was before to be the same exact molecule. Right? If this was a dash right there, then they would be enantiomer or diastereomers, right? Because this RS will change, but then this RS will stay the same.
Okay.
But we want it to stay the same, so that's why I made that into a wedge when I swapped them. And now this hydrogen is anti to the leaving group. We can grab that, make a double bond there, take that out to get the final answer here, right? But now that wedge bond is gone and it's flat and planar now because this is an sp2 carbon which is flat and planar. Right? So this is the final product here, which is Zaitsev or Hoffman?
Zaitsev.
Yeah, Zaitsev. Okay. Now let's try the top right one.
That is a strong base.
Yep, strong base, strong nucleophile. And is it unhindered or hindered?
It is hindered.
This OH minus here is considered unhindered. There are two unhindered bases that you need to know: tert butoxide and LDA. If you see any of these two, right, then that's hindered.
Oh, I thought you meant the starting material, like.
Oh,
there's
the base, yeah.
Oh, okay.
But the starting material, what kind of substrate is it? Methyl, primary, secondary, tertiary?
Secondary.
Secondary, right? So strong base, strong nucleophile, unhindered. Secondary, this is a sign of E2 reaction, right?
So you would deprotonate the carbon that has the propyl.
This hydrogen right here, which is wedge, is that anti to the leaving group?
No.
No, right? And in the other case, we rotated the single bond right here to make it anti.
Oh, but you can't rotate because it's a ring.
Yeah, you can't rotate, so you can't get that H right there. We're forced to get this H, make a double bond there, take that leaving group out to get that double bond right here. the isopropyl stays as a dash, like that.
Oh, okay.
Right? Even though this is an unhindered base, we make the less stable double bond because we cannot rotate that bond right there to make that hydrogen anti to the leaving group because it's in a ring.
Okay.
Yeah.
And the last one is bulky base
Bulky base,
and strong.
strong base, strong nucleophile, hindered, bulky. Yep. Secondary substrate.
So it grabs the terminal carbons, yeah.
To create Hoffman product, Hoffman E2. Right, different than Z stuff. Yeah, that's it for E2, SN2, SN1, E1. E2 is the hardest compared to SN1, E1, SN2 because you have to worry about the anti-peripenetration state, like if the beta hydrogen is anti to the leaving group, and if you could rotate it to make it anti or not. And also, if you have an unhindered or hindered strong base, strong nucleophile for the Zaitsev or Hoffman product. So there are like a lot more things to keep into account for E2. Zaitsev, Hoffman, hindered, unhindered base, anti-periplanar. Can you rotate it to make it anti or not? Yeah. Right.
Yeah, this
Let me
was
give
a
you
good
one
one.
more
Because
similar
I forgot
problem.
about the anti thing.
Yeah, anti-periplanar. Does the DET test that too? Because I know some classes they don't test the anti-periplanar. They just make everything flat, so you don't have to worry about that.
I forgot.
Yeah. Okay, try this one here. This is a little trick question, but let me see if you can find the trick.
So strong base, strong nucleophile, and secondary chlorine, but strong base, strong. No reaction because you would do E2, but the carbon, yeah, that one has no hydrogens.
Mhm.
And then the other one does have hydrogen, but it's syn with the chlorine, so it's not anti.
And can we rotate it to make it anti?
No, because it's in a ring.
Yeah. Right. If it wasn't in the ring and it was linear and open branch, then you could rotate it to make it anti. But because it's in a ring, we can't rotate it. No reaction. Okay. Now let's do some stereoisomer relationship. Enantiomer, diastereomer, identical. Meso, constitution isomer. Let's pull this up again. This one. Okay. 1, 2, 3, 4, 5. Okay. Okay. For each of these 5 pairs here, identify if the pairs are either identical enantiomers, diastereomers, meso, or constitutional isomers. And then let me know when you finish these 5 problems here.
I'm trying to visualize the first one. So, okay, so if I flip it down and then flip it horizontally, flipping down, does that, the stereochemistry stays the same or no?
Flipping it upside down, like where you flip this backbone starting up to down like this.
Yeah.
Yeah, it would flip the stereochemistry.
Okay, so then if you flip that down, then the BR would be a dash, and then if you flip it horizontally, that would be a wedge. Okay, so the first one is identical.
Yeah, that's the fast way to do it. When you flip it in your head, right? The slower way or the 100% for sure way to get it is the RNS to for these chiral centers here. Right? These would be the same RNS, or you could just see the flipping route within your head.
Second
3D.
one is enantiomer because all of the stereochemistry flipped.
Yep.
And then third one is diastereomer because only one of them changed, one of the stereochemistry or stereo center.
Yep.
And then the top right one is there's a plane of symmetry. So
Yeah.
is this meso?
Yeah, this is meso because meso is like identical. It's the same exact structure, but the only difference is that meso has a plane of symmetry.
Wait, but even if one is like R and one is S or something, or
Right. There is the exact same thing because when we rotate that single bond right there, the structure we get is gonna be something like this. Right. And then if I rotate this, the structure we get is gonna be something like this as well. Oh, H.
but what if they're both like R or both S?
One is gonna be R, one is gonna be S. Right? It's not gonna be both R, both S. One is R, one is S. Here for meso. Right? Because if you do RS, like this is either gonna be RS, and then the other one's gonna be the opposite version of that. Right? And these are the exact same thing because it's just rotated and there's a plane of symmetry down there. Making them identical, but it's not identical. Well, it is identical, but there is also a plane of symmetry making them meso.
And then last one is identical.
So the last one here, they have the same chemical
Wait, no,
formula.
it's constitutional.
Yeah, the last one is constitutional isomers, different connectivity.
That bromine got me because I counted it's on the third carbon and then oh wait, no, my counting is off.
What the heck? That's good.
Wait, what's the other one? Constitutional isomer. What's the other C word?
Um
So constitutional is like different.
Constitutional is
Same
different,
molecular formula, different placing.
different placement or different connectivity. Like the groups are connected differently, but they have the same chemical formula.
What's the other C word? Constitu-
For stereoisomers,
Or maybe there is no other C word.
yeah, I think it's all I can think about is identical, enantiomers, diisomers, meso, constitutional, where enantiomers, diisomers, and meso are like a type of stereoisomers. Constitutional is a type of regioisomer, and identical is just the same thing, the same molecule.
Constitution is region.
And diastereomers, another example of that is the E or Z alkenes, or cis and trans. But you can only use cis or trans if there are exactly two substituents on the alkene, exactly two groups on it. If there are more than two groups, then you use the E or Z naming system or nomenclature.
Okay.
And let's see. Okay, let's do these reactions here. Okay. Let's see. Okay, let's try these three problems here.
So the OH gets protonated.
Uh-huh. OH gets protonated by the HX, the nucleophilic acid, to create this oxonium ion, which is a good leaving group, in a product solvent because we're in acidic conditions, aqueous solution. So what would be the next step here in product solvent?
Does OH2 leave first or does Br minus
So the
attach?
OH2 plus will leave first because this will be SN1E1 like reaction since we are an aqueous product solvent. The product solvent will solve it around the positively charged OH2 plus, making that leave by itself to form a carbocation right here.
And then Br minus comes in and it's racemic.
And before that Br minus comes in, what intermediate was formed here?
Secondary carbocation. So you could do hydrogen shift.
Yep, hydride shift. Hydride shift first to make the more stable carbocation. And this dash methyl here becomes a flat planar bond because it's not sp2, where the Br minus can now come in attack that carbocation to get to the final answer here. Final answer. So always look out for a rearrangement step whenever you form a carbocation intermediate in any reaction. This is one of the reactions that can form a carbocation intermediate.
And then next one, OH gets proteinated again.
Uh-huh.
And then you have a water group that leaves.
Mhm.
And then you could do rearrangement again with the hydrate shift.
Yep.
And then Cl attacks that carbocation.
Yep. To get this final product here.
This one is OH gets protonated and then water leaves. And then you do a methyl shift.
Mm-hmm. Yeah, methyl shift in this case.
And then Br attacks that.
yeah.
Br minus.
Yep. Make sure to draw out that methyl there. Positive charge, Br minus, attack that. Final product. There. Okay. Let's end off with some hybridization bonding stuff. Oh, and 4 more charges as well. Yeah, let's actually do that. Okay. Let's look at 4 more charges first. Okay. For all of these 5 molecules here, there are missing 4 more charges. And I want you to figure out which charges are missing and on which atom for each example.
The top left one, oxygen has a -1.
Mm-hmm.
And that's it.
Yeah, that's it. Right. Because this oxygen here has one single bond and 3 pairs of electrons, where it has 1, 2, 3, 4, 5, 6, 7 electrons to itself, but it's on the 6th column. So it wants 6 electrons, but 6 minus 7 is -1. That's it. We won.
So going down, the nitrogen from CN has a +1.
Mm-hmm.
Wait, hold up. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. It's a -1, not a +1. Right?
So how many electrons does nitrogen want to itself? What column is it on the periodic table?
5.
Yeah. So it wants 5 electrons to itself, but it has 0 pairs of electrons and 1, 2, 3, 4 electrons to itself.
2, 4, 6.
5 minus 4.
For some reason, I always assume that nitrogen has a lone pair. So that's why I thought, okay, but yeah, plus.
Yeah.
And then 1, 2, 3, 4, 5.
All the pairs of electrons here are going to be given to you. If something was like this, though, what would be the charge of that nitrogen right there with 2 pairs of electrons and 2 single bonds?
5, 6 plus 1.
5 minus 1, 2, 3, 4, 5, 6. 5 minus 6.
Negative? Oh, yeah.
2 pairs of electrons, 2 single bonds.
And then, okay, so going back to that one. See, and the carbon has 1, 2, 3, 4, 5. It has -1 charge.
Wait, BRB. Okay, I am back. What would the charge be on this carbon here?
-1.
Yep, -1. This nitrogen?
1, 2, 3, 4 plus 1.
+1. This oxygen?
1, 2, 3, 4, 5, 6, 7. -1.
Negative. This oxygen?
-1 as well.
Yep, this nitrogen?
1, 2, 3, 4 plus.
Plus this oxygen?
1, 2, 3, 4. Wait, 1, 2, 3, 4, 5 plus 1.
+1. This
1, 2,
okay,
3,
that's it.
4, 5. Yeah, that's it.
Right. Okay. Yep.